Alright, let's go. Number 10. The zero-point energy problem. Max Planck wasn't trying to break physics in 1911. He was trying to patch a hole in his own blackbody radiation formula from a decade earlier, tightening the math on how oscillating atoms emit energy. Routine cleanup work. The kind no one remembers. Classical thermodynamics had one clean rule: cool a system down far enough. Remove all the heat, and motion stops. At absolute zero, an oscillator should sit dead still, holding zero energy. That was the assumption every physicist since Boltzmann had built on. Planck's corrected equations refused to go to zero. Even at absolute zero, a residual energy term stayed in the math. Not a rounding error, a floor. Experimental confirmation came decades later. In 1997, Steve Lamoureux at Los Alamos National Laboratory measured the Casimir force between two closely spaced metal plates, published in Physical Review letters, detecting attraction caused by vacuum fluctuations at separations of under a micrometer. The zero-point field wasn't theoretical anymore. It was pushing on metal. Physicists tried to make the numbers small and irrelevant. Renormalization techniques were developed specifically to subtract away infinities in these calculations. It worked for particle physics. It failed catastrophically for cosmology, when theorists calculated the vacuum energy density predicted by quantum field theory and compared it to the observed cosmological constant. The numbers disagreed by roughly 10 to the power of 120. Physicist Steven Weinberg called it the worst theoretical prediction in the history of physics. No fix has closed that gap. Every atom in your body right now at any temperature you could ever reach is jittering with energy that cannot be removed. Not by any freezer. Not by any vacuum chamber humanity has ever built. There is no floor beneath the floor. If the vacuum itself refuses to sit still, what exactly is empty space actually made of? Zero-point energy at least has a name and a measured effect. What happens next has never been directly seen at all. Number 9. The virtual particle problem. Paul Dirac wasn't hunting for phantom particles in 1928. He was trying to make quantum mechanics obey special relativity, hunting for an equation that described the electron correctly at high speed. A mathematical tidying exercise. Standard intuition said a vacuum is nothing. No particles, no fields, no activity, just an empty stage waiting for something to happen on it. Dirac's relativistic equation kept spitting out negative energy solutions, and when physicists took those seriously, the vacuum stopped looking empty. It started looking like a sea, seething with particle-antiparticle pairs flickering into existence and vanishing again. The clearest measurement came from that same Casimir effect. Hendrik Casimir predicted it in 1948 at Philips Research in the Netherlands, and it was confirmed to high precision by Steve Lamoureux's 1997 experiment, showing an attractive force consistent with virtual photon pairs briefly existing in the gap between plates before annihilating. The effect is small, on the order of piconewtons, but it is real and repeatable. Some physicists propose the particles weren't real at all, just a bookkeeping trick in Feynman diagrams, a mathematical convenience with no physical existence. That explanation collapses against the Casimir force, which physically moves metal. Others proposed the effect was purely electromagnetic and said nothing about particles, but the same formalism predicts virtual particle exchange behind the strong and weak nuclear forces too, forces that hold your atomic nuclei together right now. Every square centimeter of the empty space around you is, at this instant, hosting a storm of particles that exist for less than a trillionth of a second, before erasing themselves. Can something that has never been directly observed, only inferred from its aftermath, be called real at all? The virtual particle C is invisible. The next entry involves a particle that changes its own identity mid-flight, and for decades, it wasn't supposed to be able to change at all. Number 8. The neutrino oscillation problem. Ray Davis wasn't trying to overturn the Standard Model in the 1960s. He was trying to count neutrinos pouring out of the sun, running a detector deep in the Homestake mine in South Dakota to test a known, settled prediction about solar fusion. The Standard Model of particle physics, as built in the 1960s, treated neutrinos as strictly massless. Massless particles cannot change identity over time. The sun should produce electron neutrinos, and Davis's detector should count exactly the number the solar models predicted. He counted about 1/3 of the predicted number, consistently, for over 2 decades. The solar neutrino problem sat unresolved for 30 years. The resolution came from the Sudbury Neutrino Observatory in Ontario. In 2001, the SNO collaboration, led in part by Arthur MacDonald at Queen's University, published results in physical review letters demonstrating that the missing neutrinos hadn't disappeared. They had switched from electron type into muon and tau type mid-flight, a process called oscillation that is only possible if neutrinos carry mass. Physicists first suspected a flaw in the solar model itself, adjusting core temperature and fusion rate assumptions. The numbers wouldn't cooperate. Others suspected detector inefficiency at Homestake. Independent detectors in Japan and Canada reproduced the deficit. The final holdout, that neutrinos were simply massless as the standard model demanded, fell only when SNO caught the missing particles in their new disguise. MacDonald and Takaaki Kajita shared the 2015 Nobel Prize in Physics for the discovery. Trillions of neutrinos are passing through your body as you watch this, right now, silently switching identities inside you. And you will never feel a single one. If a fundamental particle can rewrite what it is without any external cause, what does identity even mean at the smallest scale of reality? Neutrinos change form. The next entry describes a particle with no form at all until you force it to choose one. Number 7. The electron cloud problem. Erwin Schrödinger wasn't trying to erase the electron's location in 1926. He was trying to fix Niels Bohr's atomic model, which had electrons orbiting the nucleus like tiny planets, a picture that already conflicted with known spectral data. Classical physics, and even early quantum theory, assumed a particle has a definite position at every moment, whether or not anyone is looking. Schrödinger's wave equation produced not a location, but a probability distribution, a cloud describing where the electron is likely to be found, with no fixed position until a measurement forces one. Max Born, at the University of Göttingen, published the statistical interpretation in 1926 in Zeitschrift für Physik, proposing that the square of the wave function gives the probability of finding a particle at a given point. Experimental confirmation followed from decades of scattering and diffraction experiments, and Born received the Nobel Prize in Physics in 1954 for the interpretation. Einstein rejected it outright, insisting the electron must have a real, hidden position we simply hadn't measured yet, a hidden variable theory. John Stuart Bell at CERN devised a testable inequality in 1964 that could distinguish hidden variables from genuine indeterminacy. Experiments by Alain Aspect in France through the 1980s, and later by groups closing every remaining loophole through 2015, violated Bell's inequality every time. Hidden variables, in the local sense Einstein wanted, are ruled out. Every electron and every atom that makes up your hand has no defined location right now. Not unknown to us. Undefined. Until something, anything, interacts with it. If the smallest pieces of your own body have no fixed position until observed, what, physically, are you made of between observations? An electron has no location until forced into one. The next entry involves particles crossing barriers they are not supposed to be able to touch at all. Number 6. The quantum tunneling problem. George Gamow wasn't trying to explain the sun's fuel source in 1928. He was trying to understand alpha decay, working out why certain unstable nuclei spit out alpha particles at energies that made no classical sense. Classical mechanics is unambiguous. A particle without enough energy to climb over a barrier cannot get past it. Full stop. No exceptions. A ball without enough speed rolls back down the hill every single time. Gamow's quantum calculations showed the alpha particle didn't need to climb over the barrier at all. It had a non-zero probability of simply appearing on the other side, as if the wall weren't fully solid. Gamow published the theory in 1928 in Zeitschrift für Physik, and it was independently derived the same year by Ronald Gurney and Edward Condon in the United States. The mechanism turned out to be essential to stellar fusion inside the sun's core at a temperature of about 15 million Kelvin. Protons lack the classical energy to overcome their mutual electric repulsion and fuse. Physicist Fritz Houtermans and Robert Atkinson calculated as early as 1929 that without tunneling, the sun's core would be too cold for fusion to occur at any meaningful rate. Some physicists initially treated tunneling as a mathematical artifact specific to alpha decay, not a general phenomenon. That explanation failed once tunneling was confirmed in entirely separate systems, the tunnel diode. Built by Leo Esaki in 1957, and scanning tunneling microscopy, developed by Gerd Binnig and Heinrich Rohrer at IBM Zurich in 1981, both of which won Nobel Prizes. Without this barrier-defying leak, the sun's core would fuse hydrogen millions of times more slowly than it does. Every photon of sunlight warming your skin exists because a proton, at some point, cheated a wall it had no classical right to cross. If particles can bypass barriers that should be absolute, is any boundary in physics actually a wall, or just a very strong suggestion? Tunneling breaks the rules of energy. The next entry involves a force that should break a fundamental symmetry of nature and simply refuses to. Number 5. The quark confinement problem. Murray Gell-Mann and George Zweig weren't trying to trap anything in 1964. They were independently trying to organize a chaotic zoo of newly discovered subatomic particles into a simpler underlying pattern, and both proposed that protons and neutrons were built from smaller constituents. Once quarks were proposed, the obvious next step was to isolate one. Every other fundamental particle discovered up to that point, electrons, photons, even individual atoms, had eventually been isolated and studied alone. No one has ever done it. Every experiment designed to knock a single quark free instead produces a spray of new particle pairs. The quark never comes out alone. Deep, inelastic scattering experiments at the Stanford Linear Accelerator Center between 1967 and 1973, led by Jerome Friedman, Henry Kendall, and Richard Taylor, confirmed quarks exist inside protons by scattering high-energy electrons off them. The trio won the 1990 Nobel Prize in Physics. Yet in every one of these, and every subsequent experiment, quarks appeared only in bound states of 2 or 3, never alone. Physicists proposed the confining force simply gets weaker at short range and might eventually let a quark escape at high enough energy. The opposite happened. David Gross, David Politzer, and Frank Wilczek showed in 1973 that the strong force does the reverse of every other known force. It grows stronger as quarks separate, a property called asymptotic freedom, for which they shared the 2004 Nobel Prize. The energy required to pull two quarks apart increases without limit until it becomes cheaper for the vacuum to spontaneously create a new quark pair than to let one quark travel free. Every proton in every atom of your body is built from quarks that have never once, in the history of the universe as far as anyone has measured, existed alone. If a fundamental particle can be proven to exist yet can never, even in principle, be isolated, in what sense is it truly a separate object at all? Quarks cannot leave their prison. What's stranger is that inside that prison, most of the mass and the spin isn't coming from the quarks at all. Number 4. The proton spin crisis. The European muon collaboration wasn't trying to start a crisis in 1987. They were trying to confirm a routine prediction that a proton spin comes from the combined spin of its 3 constituent quarks, adding up in a simple, expected way. The quark model predicted quark spin should account for essentially all of the proton's total measured spin of 1/2. This was considered settled physics, textbook material, not something anyone expected to test and fail. The MC experiment at CERN found that quark spins account for only a small fraction of the proton spin, later refined by multiple experiments to roughly 30%. 70% of the proton spin was simply unaccounted for. The original result was published in 1988 in Physics Letters B by the European muon collaboration, led by John Ashman, and became known as the proton spin crisis. Follow-up experiments at the Hermes detector at Decay in Germany and the RHIC collider at Brookhaven National Laboratory through the 2000s confirmed the deficit was real, not a measurement artifact. Physicists proposed the missing spin comes from gluon spin, the force carrying particles binding the quarks. Measurements at RHIC found gluon spin contributes real but insufficient amounts. Others proposed orbital angular momentum, the quarks and gluons physically circling each other inside the proton. This appears to account for some of the remainder. But as of ongoing measurements at Jefferson Lab, the full spin budget still does not close cleanly. The proton is the single most common particle of ordinary matter in your body and in the universe, and physics cannot yet fully account for where 70% of its most basic quantum property comes from. If the simplest stable building block of matter still hides most of its own spin. What else are we assuming we understand about it? The proton hides its spin. It may also be capable of doing something that has never once been caught happening, quietly falling apart. Number 3. The strong CP problem. Roberto Piche and Helen Quinn weren't trying to invent a new particle in 1977. They were trying to patch an embarrassing gap in quantum chromodynamics. The theory of the strong nuclear force at Stanford University. The mathematics of the strong force theory permits a term that would violate charge parity symmetry, meaning the strong force could, in principle, treat matter and mirrored antimatter differently and induce a measurable electric dipole moment in the neutron. Every precision measurement of the neutron's electric dipole moment has come back at, or indistinguishable from, 0. The theory allows violation on the order of 1 part in a billion or larger. Nature shows a violation smaller than 1 part in 10 billion, and possibly non-existent altogether. The most recent neutron electric dipole moment measurement, published in 2020 by the NEDM collaboration at the Paul Scherrer Institute in Switzerland, constrained the value to below 1.8 times 10 to the negative 26 electron centimeters, consistent with exactly 0. Peche and Quinn's 1977 paper in Physical Review Letters proposed a new symmetry that would force this term to 0 dynamically, predicting a new particle as a side effect, the axion. No axion has ever been detected, despite dedicated searches including the AtomX experiment at the University of Washington running continuously since the 1990s. Some physicists propose the CP-violating term simply has a value of 0 by pure coincidence, with no underlying mechanism, a solution most theorists reject as an unexplained fine-tuning, since nothing in the mathematics requires that coincidence. You are made of neutrons that, according to the equations governing the force holding their insides together, have every right to carry a measurable asymmetry between matter and its mirror image. They carry none that anyone has ever found. Why does one of the 4 fundamental forces obey a symmetry it isn't required to obey? For a reason nobody can confirm? The strong force is suspiciously well behaved. The final entry concerns a decay the same force may permit, a decay that would mean nothing is actually permanent. Number 2. The proton decay problem. Howard Georgi and Sheldon Glashow weren't trying to threaten the stability of matter in 1974 at Harvard University. They were trying to unify the strong, weak, and electromagnetic forces into a single mathematical framework, a grand unified theory, tidying up the Standard Model's 3 separate force equations into one. The Standard Model treats the proton as absolutely stable, protected by a conservation law called baryon number. Under the Standard Model alone, protons should never decay. Not in the current age of the universe. Not ever. Grand unified theories require that baryon number conservation breakdown at extremely high energies, which mathematically forces the proton to become unstable with an enormous but finite predicted lifetime. Georgi and Glashow's 1974 paper in Physical Review Letters predicted a proton lifetime around 10 to the power of 31 years. The Super Kamiokande detector in Japan, a tank holding 50,000 tons of ultra-pure water watched continuously since 1996, has never recorded a single confirmed proton decay event, pushing the experimental lower limit on proton lifetime past 10 to the power of 34 years for the primary predicted decay channel, according to results published by the Super Kamiokande collaboration in Physical Review D. The simplest grand unified theory, based on the mathematical group SU, is now considered ruled out by this null result. Physicists proposed more complex unification models with longer predicted lifetimes, including supersymmetric variants. These remain untested, since no facility has run long enough, or built a large enough detector, to reach the new predicted thresholds. Every proton and every atom in your body may be, at this very moment, running an internal countdown so long that the universe itself is still young by comparison. a countdown physicists still cannot rule out. If matter is not eternal, only extraordinarily patient, at what point does stable simply mean hasn't happened yet? 9 entries down, and every one of them assumed a smooth, continuous stage on which particles perform. The final entry says the stage itself may be lying to you. Number 1. The quantum foam problem. John Wheeler wasn't trying to dismantle the concept of empty space in 1955 at Princeton University. He was trying to reconcile general relativity with quantum mechanics, working through what happens to spacetime's geometry at the smallest conceivable scales the math allowed. General relativity treats spacetime as smooth and continuous at every scale, a flexible fabric that bends but never tears, never fluctuates on its own. Wheeler's calculations suggested that at the Planck scale, a distance of roughly 1, 6 times 10 to the negative 35 meters, quantum uncertainty should make spacetime's geometry itself fluctuate violently, foaming with microscopic wormholes and shifting topology. Wheeler introduced the term quantum foam in a 1955 paper in Physical Review, and the idea has remained a cornerstone prediction of quantum gravity theories ever since. Yet the Planck scale is roughly 10 to the power of 20 times smaller than anything the Large Hadron Collider can probe, placing direct detection permanently, or at least currently, out of technological reach. Physicists proposed indirect tests using distant gamma-ray bursts, reasoning that foam-induced fluctuations should blur or delay light traveling billions of light years. Observations by the Fermi Gamma Ray Space Telescope, published by the Fermi Collaboration through the 2010s, found no such blurring down to precisions far tighter than simple foam models predicted, ruling out the simplest versions of the theory without ruling out the concept itself. Some theorists have proposed the foam is real, but far gentler than Wheeler's original picture. Others question whether space-time is fundamental at all, rather than an emergent structure built from something else entirely. The empty space between every atom in your body, at a scale 100 billion times smaller than a proton, may not be empty, or smooth, or even continuous at all. It may be foam, and no instrument humanity has ever built can zoom in far enough to check. If the fabric of reality itself might not be a fabric at all at its smallest scale, then what exactly are we standing on? The universe is not confused. It has never once failed to follow its own rules. We are the ones still guessing at what those rules are, 10 separate times over, from the edge of the vacuum down to the geometry of empty space itself. Every entry on this list did not come from some exotic corner of physics. It came from the center of the most tested, most confirmed theories we have. The atoms that make up your hand, your breath, your thoughts are running on physics we can predict to 11 decimal places and still cannot fully explain. If the best tested science in human history still can't tell you what you're made of at the smallest scale, what exactly is the ground beneath your feet? If you want to see more videos like this, click the video on screen now.